Great. So our first speaker today is Dr. Valdir Novello, who is a postdoctoral researcher at the University of Tübingen in Germany. He studied physics and natural sciences at the University of Sao Paulo, and his current research interest is primarily concerned with reconstructing the South American monsoon using geochemical stalagmite records. But he also has experience in the fields of cave monitoring, environmental geochemistry, archaeology, paleomagnetism, and atmospheric sciences. So with that, take it away.
Thank you. First, thank you for the invitation to give this presentation here. So today I will talk about how to interpret δ13C, but as many of you guys know, it's quite complicated to interpret δ13C in spatial terms, sometimes even it's impossible, I would say. And it's δ13C different from δ13U, is very cave specific, sometimes very stalagmite specific. So from different stalagmites from the same cave, you can have a completely different sign. Because of that, I will give some to interpret that. Sometimes you go, your interpretation only works for that stalagmite or for that cave. So I will give you at the beginning of my talk an overview about δ13C, but the second part of my talk I'll be focused on a specific example how we interpret δ13C some specific sites here in South America. So Max already presented these equations to you yesterday, so about the solution of the limestone and then the precipitation of calcite here. So to be able to interpret our carbon, our δ13C, we need to understand where this carbon comes from. Well, our carbon is here in our stalagmite, this calcium carbonate here. If we look back to the equation, this carbon will be here in the bicarbonate, and then before here, it will be here, okay? And then we have a carbon here in the limestone. So we have one of the carbon coming here from the limestone, and then we have also carbon here in the CO2. Then the question is, where did CO2 come from? Well, the CO2, we have CO2 in the soil, and then we have also CO2 in the atmosphere. The amount of CO2 in the soil is much higher than the atmosphere, so the importance of here is much higher. But there is a small contribution from the bedrock, for the limestone or limestone, and also from the atmospheric CO2. So first, let's talk about the CO2 we are in the soil here. Well, then where does CO2 on the soil come from? Pretty much from the organic matter, and then which come from the vegetation. And then when you look to the vegetation, we have at least two types of vegetation. Our vegetation will do photosynthesis in two different ways. Plants C3, or for metabolism C3, and plants C4. C3 metabolism is more common in trees, and C4 is more common in grasses. And the isotopic composition, the δ13C values in this kind of C3 plants and C4 are different and not overlap. Like the δ13C in C3 plants will be ranging between -22 and -32, and C4 plants will be -9, -17. And so if you have a forest, you probably have more C3 plants. If you have like an open field, you probably have more grasses. So the isotopic composition of the organic matter here will be more negative in this environment, more positive in this environment here. But there's also some complications on that, because there's exceptions as well. There are trees which perform metabolism C4, and there's also grasses with metabolism C3. Another thing we complicate to interpret vegetation using δ13C is this kind of plant, the plants come, which is cactus in general, because there's a topic composition of the cactus is ranged between -10 and -28, which overlap C3, C4 plants. So when you have cactus, you basically have a mixed sign. But anyway, you provide the CO2 to your soil, which will dissolve your limestone, which will go to your stalagmite. So what's happening on top of your cave, the change in this kind of vegetation, this kind of environment will be affected by δ13C. And then we can go to atmosphere. I think in this paper here, Brecker 2017, is a good, provide a good, let's say, ideas about how the δ13C in the atmosphere, how the amount of CO2 in the atmosphere affect the δ13C in your stalagmites. Here in the top, for example, you see the variability of the amount of CO2 in the atmosphere over the last 500,000 years. We know, like, due to glacial, interglacial periods, we have a change in the CO2. CO2 is high during interglacial periods, like the Holocene here, and more lower during glacial periods. And then C3 plants are affected, the isotopic composition of C3 plants, the δ13C of these plants, are affected by the δ13C values on the CO2 in the atmosphere, and also the concentration of the CO2 in the atmosphere by this equation here. So this delta is related to the concentration of CO2 in the atmosphere. This is the isotopic composition of the CO2. So if you change the isotopic composition of CO2, if you change the concentration of CO2 in the atmosphere, this will affect the δ13C values in your plants, which will provide these values to the soil as well. Here in black is a reconstruction of the average global δ13C in C3 plants, you see here in black, and in red here is the average δ13C from stalagmites. As you see from the last 100,000 years, there's a good fit in what was predicted to be the δ13C in plants and what the values was found in stalagmites around the globe, the compilation. The reason we have a good fit here in the last 100,000 years is because we have much more records during this time period than the older time periods here. And also, but this shift we can see here between the glacial period, the last glacial maximum to the Holocene, will be around -2 per mil. So if you have in your stalagmites a shift around 2 per mil between glacial and interglacial period, maybe is connected with the variability of CO2 in the atmosphere, we are affecting the δ13C in the plants above your cave. Okay, but keep in mind only 2 per mil. Then as well, we can have organic carbon, also inorganic carbon, for inorganic source or organic source. Inorganic carbon present higher values than organic carbon because of the photosynthesis. Photosynthesis concentrates more carbon-12, so in general plants has δ13C value is -20, and inorganic carbon has positive values sometimes. So if you have more organic material, which means more organic carbon in your soil, you have more negative values in δ13C. If you have less organic material, you can also have more inorganic carbon there in your sediment, provide more higher values in δ13C in the soil. Okay, so everything I was talking until now happening above your cave, in the atmosphere or also in the soil, in the vegetation here. But then you have many effects on the δ13C, which is connected with it happening inside of the cave or the epikarst. Here's a list of some of these effects. You have pre-calcite precipitation, pre-aragonite precipitation, if you have aragonite samples. We can have an open-closed system like Max explained yesterday. You can have different sources, you can have different soils, you can have your limestone with the different isotopic composition of δ13C. Then you have kinetic fractionation that happens during the precipitation of your stalagmite. Everything here will be affecting the δ13 values in the stalagmites at the end. I go quickly to talk about each one of these. So first, what's pre-calcite precipitation? Well, pre-calcite precipitation or pre-aragonite precipitation is all calcite or aragonite which was precipitated before your stalagmite. Well, we have the seepage solution going on here, dissolving your limestone, and then putting calcium in solution. Then you have the dripping water here, you start to precipitate your stalagmite. But if you have a precipitation of calcite in these fractures here, or in the stalactite here, this first precipitation, like the calcite, you like more the carbon-12, you say it's first calcite, calcite in general. Since they like more this carbon-12, well, they take the carbon-12 in the first precipitation, and which will increase the concentration of carbon-13 in the solution here. Since you are increasing the concentration of δ13 solution, your sputum will have more higher values of δ13C. But when this happens, what you need to precipitate more calcite before a stalagmite? You need to have, let's say, if you look at the equation here, when you precipitate these speleothems, you need to remove CO2, you need to remove water from the solution. So if you are removing water in the fractures here, removing CO2, if you have degassing of CO2 in this fracture, you are precipitating speleothems in these fractures here. This happens in the roof of your cave here in the ceiling. When the dripping water here finds the atmosphere inside of the cave, usually the atmosphere inside of the cave has less CO2 than your solution. Then you have the degassing of CO2 here. You start to precipitate your stalactite, which you concentrate here more carbon-12 here, and you release more carbon-13 to your stalagmite. If you have more drier conditions, you have more empty space in these fractures here, which will lead to more degassing, more loss of water of the solution. So you precipitate more calcite here in the fractures. So in a drier period, you increase your PCP, which will increase the δ13C here in your stalagmites. Another example, PCP also happens inside of stalagmite, or inside not, but in the surface of stalagmite. Like here in Brazil, Nicholas and I, have been monitoring caves in different parts. We put glasses like this to simulate the surface of stalagmite to precipitate fresh calcite. So we have the dripping water going on here. We start to accumulate calcite here, aragonites among the caves. And then a couple of weeks, sometimes a couple of months, we remove these glasses here. We replace this glass, put a new glass there to collect the new calcite. Then we analyze the isotopic composition of this material. Here's one example. Then we do a transect of analysis here. We start to analyze to one border to another border here, what you see here. Like this point 1 was the δ13C. Here we're analyzing one border of this glass. This point 5 here was analyzed here in the middle. And this point 9 was the other border here. So when we look at the δ13C, this transect here, first we see the δ13C values in the middle of the glass is more negative of the values in the border here. This happens because first, when you have your dripping going on here, you first precipitate calcite in this part, then your solution, you move here to the border, you precipitate calcite in this glass here until the border. Since you precipitate first the carbonate here, you have more carbon-12 in this middle part. And then in the border, you have more carbon-13. So you have a pure calcite precipitation here in relation to here. So we have this fractionation going on here. But if you think this solution was also dripping from the ceiling, or was also dripping from your stalactite, the same was happening before, in the epikarst in your stalactite. So we have this PCP going on from the entire epikarst until here. And then also in your stalagmite. And then if you do a test in your stalagmites, you sample in the same layer, the isotopes, the same layer, you probably see something like this fractionation to the borders, which is related to the PCP. Max explained that yesterday, using this, how he created these conditions in his lab as well, precipitated calcite in his lab. So this is the natural environment. Okay, this was PCP, which can also be related to our next topic here, next item, which is open versus closed system, which also Max explained yesterday. Thanks, it was making my life easier here. Well, open system is when your solution here is a constant contact with CO2 here in the soil. Since the CO2 concentration in the soil is very high, you have almost an infinite source of CO2 because we can never remove all CO2 from the soil by the solution here. If you have this constant contact with your solution with the CO2, you have enough, let's say, acidity in your solution to keep dissolving the limestone here. But if you close your system, if this solution loses contact with the CO2 in the soil, your solution starts to dissolve the limestone. At some point, your solution becomes neutralized. It's not acid anymore. Then you stop to dissolve your limestone here. But when it's dissolving your limestone, you are incorporating new carbon from the limestone here to your solution. If you stop this solution, you stop it to take carbon from the limestone here. But most of the time, the carbon from your limestone is much more positive than the carbon you have in the soil. You have much more carbon-13 here than here. These are inorganic carbon here. So if you change it from an open system to a closed system, you are changing the isotopic composition of your carbon in your stalagmite. Most of the cases are a mix between open and closed systems. Okay, so this can change over time in the same place. You can have just one or other, but most of the time you have both things going together. And related to that, we have different sources. Most of the sources are CO2 from the soil or your limestone here for the carbon. You can have more contribution to one, more contribution to another, which is related to open and closed system. But sometimes, like this is an ideal case, okay? You can have the other source of carbonate on top of your cave, could also provide a different isotope signatures for your stalagmite. Depending on how much this contributes to your solution, you can have a different sign over time as well. And then we go to the effects that happen during the precipitation of the carbonate in your stalagmite here, which involve effects of temperature, like if you have your spiritum be precipitate at different temperature, the fractionation naturally happens between the solution and the solid phase, which is the carbonate. You change if you change the temperature. So if you are moving at a temperature, the fractionation will change. Okay, how much you fractionate from the solution to the solid phase. If you force your reaction, like if you force the CO2 degassing, or if you have a strong evaporation, this also forces the precipitation of your stalagmite. If you are forcing this, you are increasing this kinetic effect. Basically, you are precipitating calcite in disequilibrium. If you are precipitating calcite in disequilibrium, probably your values will be, or isotope values both from carbon and oxygen will be quite higher, because the equilibrium effect will affect the carbon and the oxygen more or less the same way. Okay? So considering we have all these effects going together all the time in your speleothems, in your cave, it's possible to interpret δ13C. Well, the answer for that is depends, and depend in also because many of these effects provide the same let's say, behavior in your variability of your δ13C. For example, they have a similar response. If you have drier conditions, you increase your PCP. Also, you increase the evaporation, which will increase the kinetic effects. If you have a long time, you have like say for 1,000 years, you have more dry period than it was in the previous time. You're basically favoring C4 plants than C3 plants. Like grasses go better in a more dry condition than C3 plants. And C4 plants has more higher δ13C values. Also, with more drier conditions, you have less organic material in the soil. So in a dry period, you have everything together here. It's everything in this list here. You provide higher δ13C values to your stalagmite. So you have a long dry period. You have everything being come together here. Then you have more δ13C. So sometimes you can interpret the δ13C as a proxy for local hydrology, not because it's raining more or less, but because in a dry period you have everything is going on together here, which will provide more higher δ13C for your stalagmites. In a wet period, you basically go to all the directions, the values will be lower. So then you can also have a correlation between δ13C, δ18O, if your δ18O is related to the amount of precipitation, the amount of effect as well. Okay? So using this mechanism here, we apply this idea to interpret all these records here in South America for the last 2,000 years, which was presented in this paper here. And then why 2,000 years, not all other time scale? Actually, when I submitted this paper, the reviewers asked that, why do you not need for all time scales if you have this stalagmite? Why you just choose the 2,000 years? The answer for that is because it's easier. Because when you look to those 2,000 years, the boundary conditions, the climate boundary conditions, was pretty much the same. You don't expect here in the tropical region in South America, big change in temperature during 2,000 years. When I talk 2,000 years, I'm more focusing between the year 0 and the pre-industrial time. The amount of CO2 in the atmosphere was the same. We didn't have a variability of CO2 in the atmosphere during this time period. The natural vegetation didn't change much. There's not enough time to really have a significant change in vegetation. So a lot of things affecting your δ13C was constant. So since it's constant, if you have what was changing in your in the climate conditions during 2,000 years, was pretty much the amount of precipitation, the hydrologic conditions. So since you can, some of your temperature was constant, the amount of soil above the cave was probably constant, we don't expect strong additional effects on δ13C. Then we compiled more than 20 stalagmites. So the list is here. And first, to investigate what was driving δ13C in many of these different sites. It's not clear to see here, but this is a plot from the modern δ13 values from the top of the stalagmites comparing with the annual precipitation of different sites. So each dot here is one site. You will see when you increase the precipitation, the δ13C was more negative here. This indicates when you have more precipitation, where's the place where having less PCP. When you have more places where more drier, you have more higher δ13C because you have more PCP than places. The correlation here was pretty high, was 0.7. It was very significant. And also was quite significant the correlation with temperature of these regions. Like the δ13C is higher when you have more higher temperature as well, because this is more connected with some kinetic effects going on. In more drier and hot places, you have more kinetic fluctuations. Okay, so we have an effect related to the local hydrology here, but also related to the temperature talk spatially here in this region. And then try to understand this together, like as in the entire continent. We did the PCP from the δ18O, which is here in South America is a proxy for the monsoon intensity, and the δ13C, which you had just presented before. And we see the δ18O, like the principal components of the δ18O and δ13C, they go quite well together most of the time until the pre-industrial times here. Since the principal components, we can consider this an index for the monsoon intensity. Well, we have more negative values, the monsoon was stronger. And the δ13C, we are considering here a proxy for local hydrology. Since the two curves go more or less well together, this indicates to us the local hydrology is connected to the monsoon. But this is not true when we look for the last 200 years here. Well, our interpretation here was the monsoon and local hydrology of δ13O or δ13C was not connected in the last 200 years because we changed the boundary conditions. Because in the last 200 years we increased the CO2 in the atmosphere, we increased deforestation, anthropogenic deforestation, we are increasing the temperature in the planet. So all these things are affecting δ13C was not really connected to hydrology anymore. But in the past was, because these others it was constant. Okay? And then when you look spatially the correlation between δ13C at different sites, we pretty much see the same we see in the δ18O. We have a climate dipole in South America, from the west part of South America here, going to the northeast part of here, which is connected to climate dipole here. When we have strong precipitation in this region, we have a more drier conditions region here, is vice versa. Okay. I was considering δ13 is connected a lot of processes happening in the soil. All these parameters you see, this is the δ13C of the stalagmite, Valdir cave. And all these parameters here are magnetic properties of this stalagmite. Plínio Jaqueto will talk about this tomorrow, so I'm not going into details how these magnetic minerals are preserved or how it provides magnetic signature to your stalagmite. But what I want to show you here is a lot of these magnetic minerals are connected with the process happening in the soil, which also affects your δ13C. So we see a good correlation between magnetic intensity in the stalagmite with the δ13 values. But Plínio will talk more in detail about this tomorrow for you. Okay. So that I present to you what we basically interpret all different records together, only for the last 2,000 years. Now, since δ13C is very site-specific, I go more in detail in individual sites. I will be talking about these three sites here. One here in Jaraguá Cave, Lapa Sem Fim Cave, the other caves here in Rio Grande do Norte State. Here, this region here is the Cerrado do Mine, this kind of vegetation, is the Brazilian savanna, which look like this. Sometimes you see some open fields, sometimes some kind of dense forest. This change over time periods. So you can have more this or more this. In the same figure, you can see here some open fields, some forest, to the savanna. We are in this transition between the Atlantic forest, the savanna, Brazilian savanna here, which we call Cerrado. The first site I will present to you is this one, in the South Pantanal region, in the, let's say, west part of the Brazilian Cerrado, here, which is this record here. This is the δ18O from stalagmites going from the present until almost 30,000 years ago. Each color here is one stalagmite, Here's the delta-18O, here's the delta-13C. We are quite confident to interpret the delta-18O in this region as a proxy for the monsoon intensity. I will explain why in the next slide, but our focus here is on the delta-13C. Okay? As I present to you, a lot of times the delta-13C, delta-18O, they correlate between them. So we are expecting, when we analyze the stalagmites, to have a good correlation as well between delta-13C, delta-18O, because we see that in many different stalagmites. But when we look at this figure, we see actually that they were anti-correlated in the same stalagmite, the same analysis. The delta-18O was getting more positive, the delta-13C was getting more negative. So then we say, okay, what's happened here? Why they're so different? And what's I think I found more amazing in delta-13C here is clearly see a abrupt shift here. To have this shift in the same stalagmite, something happened. This shift was quite large, it was 10 per mil, more than 10 per mil. Go for 2 positive to minus 10. So something happened in this environment to provide this complete shift. Like the previous stalagmite, the values was always high, and then the modern stalagmites much lower, negative 13 values. First thing we need to test here, our source of our carbon. Where does carbon come from? One of the sources is the limestone. So we collected pieces of the limestone of that cave, we analyzed delta-13C that limestone, and we find the values was around 1 per mil positive, which is pretty much similar to the values we have in stalagmites during the glacial period. Considering when we have our organic source, we have soil, we have organic material, vegetation, we expect to have more negative values in the delta-13C. To have very high positive values like this, probably have a strong contribution from the bedrock. But this was just an idea, so we need to test that. But also, when you look to geochemical models, like Max was presenting yesterday, if you have C4 plant glasses above your cave, you can expect a range of delta-13C values between 2 positive and minus 6. So these values here from the glacial periods is also constant C4 plants above your cave. If you have the C3 plants above your cave, we can expect values lower than minus 6. So these values are here from the Holocene period for the modern values of the stalagmites is constant if you have C3 plants above your cave. So one alternative explanation for this shift could be a change from C4 plants or C3 plants. So it was a second hypothesis. Then, looking to the delta-18O, another idea we had was, well, considering the more negative values indicate stronger monsoon, maybe because of a stronger monsoon, this monsoon was eroding above the cave, with removing everything on top of that. Because of that, we don't have soil, we don't have organic material enough to the values get negative. So this was another idea. So then we try to test these ideas. Just a parenthesis here to explain why we're interpreting the delta-18O as a proxy of the monsoon. Here's a comparison between our record in this start with the other delta-18O records in South America, the point 5, 6, and 8. Here is our stalagmite. The all then show more delta-18O more negative during the glacial period, more positive during the Holocene period, which connected with insolation, higher insolation during the glacial period, lower insolation of the Holocene. But also, there is an independent proxy here, which is the point 7, which is not stalagmite, it's a salar dune in Bolivia, where they have this proxy with alpha content in the salar, which is also a proxy for hydrology. They also showed a glacial wet and Holocene dry here. So our proxy delta-18O was quite constant, so we were not have much doubts about the delta-18O. We're trying to understand what's happened in delta-13C. Looking to the cave, then to understand the source of your carbon, you need to understand your system, you need to understand your cave. This was Jaroga Cave. The cave has a small entrance, it's the vertical profile of the cave. And we are lucky because we find a lot of sediments inside of this cave. So since we are talking about changing vegetation, changing the soil, we have soil inside of the cave. We say, okay, no, we need to check the soil. We need to check what's happening in the soil, because we never had soil inside of the cave. What you have inside of the cave is sediment. Soil is when it's in situ, when you transport the soil, it becomes sediment. So we have sediment inside of the cave, but this sediment was soil above the cave at some point, because this kind of material is not formed inside of the cave. And then we start to look outside as well. So considering our delta-13C, our modern delta-13C is quite related with C3 plants, we will try to check the vegetation of the cave, which look like this. Then I, together with Plinio, which is here, we collect the different plants above the cave. We did the transect, collect the different species of plants. We analyze the δ13C of these different plants. We find most of the plants, except one, was citrus plants, which present the δ13 values around -30. Okay, which is very negative. So it's consistent to our interpretation, we have more citrus plants during the Holocene period. And then we dig a trench inside of the sediment inside of the cave. This is Plinio again. He was digging there with me many times. And we were lucky because we started to date the sediment applying different techniques. We use thermoluminescence, we use uranium some carbonate layers in the sediment. We use carbon-14 bioapatite, but the best result we have for the age was carbon-14, the organic matter of the sediment here. And the age was pretty much the same range we have in the stalagmites. And one interesting thing is just looking by the sediment is the top part, the Holocene, where I think we have more soil and more vegetation above the cave, was dark, which already indicates it was more organic material in the Holocene period here. And also the sedimentation rate, when you look here, was much higher than the glacial period. In the Holocene, the deposition of the sediments was quite low. We did the XRF in the sediment, just to understand also the source of the sediment. We find two groups of elements. One group relates more with cyclastic deposition. Another group here relates more chemical compounds, like more organic compounds like phosphorus, for example. I will explain a couple of slides why I'm presenting this, okay? We try to combine different blocks to understand the δ13C. So then we also analyze strontium in stalagmites. This I will explain better this strontium later for you. And we also was looking here because we find this isotope signature of the strontium from the limestone and from the soil was quite different. Like in the soil we have strontium values around 0.715, which is high, and in the bedrock we have values around 0.708 here. And the values we find in stalagmites was something between. So we have two different sources of strontium here, more limestone or more soil. And then we put everything together. These three records here was measured in stalagmites. These three records, proxy here was measured in the sedimentary profile here. One thing I want to bring your attention is the relationship between the δ13C we measure in the stalagmite with δ13C we measure in this sediment. So this we measure δ13C in the organic material of the sediment. And when we look, we see the same shift here. And also the range is quite similar, which means then here in the sediment, the organic material, we don't have all that effect I was explaining to you what happened in your stalagmite. These are pure organic material, so it was pure sign of the vegetation of the cave. So considering the similarities between these two records, pretty much what we see in the stalagmite, what was transferred for the vegetation here, was basically transferred to the stalagmite, this δ13C. And related to that, we also increase the organic compounds when we go more close to the ocean, we can see here, okay? And when we look to strontium, which is approximately for more contribution from the bedrock, more contribution from the soil, in this case here, we see more contribution from the bedrock during the glacial time, and more contribution from the soil during the Holocene time here, which also indicates to us we have probably much less soil in the glacial period, which is also consistent, for example, if you have more rain or more erosion during the glacial period, you'll be basically claiming above your cave, which, let's say, also not provide you the opportunity the vegetation go up much there. So we have a complete change of the system, with a system from C4 plants to C3 plants, with less soil, more soil, happened between glacial and the Holocene. Which, surprisingly, was not expected when you look at the δ13O, because in the glacial period it was more wet period. So we expect to have more vegetation when you're wet period. So it's not the case here. To check if it was something local, which happened only on top of the cave, or if it was something more regional, we compared pollen records from that region. It's not too close, it's some 100 kilometers from that cave, but it's the nearest pollen record we found. It's from Laguna Lagaiba. And the plotting records also indicates to us a shift in the type of vegetation during the glacial to the Holocene period, going from the savanna pollen here to more semi-decidual tropical forest in the Holocene. Okay, so we have a kind of tropical forest appearing in the Holocene period, and more plants related to the savannas appearing in the same time period here. The same time when we have the shift of δ13C. So what provided this change in the vegetation, like this regional change in the vegetation? One of the hypotheses was temperature was increasing, is the delta TO from ice core in Antarctica, which is a proxy for temperature in the southern hemisphere, and the CO2 in the atmosphere was increasing. Here I reverse the scale, the CO2 was increasing. So at the same time the CO2 of the atmosphere was increasing, we have this shift in our vegetation proxies here. But remember when I presented at the beginning of my talk, when you change the CO2 in the atmosphere from the glacial to the Holocene, we expect an effect in your stalagmite of 2 per mil. But here we have more than 10. Okay, so the like direct effect of CO2 maybe was responsible for 2 per mil here in the variability, but the other was connected to the vegetation, and probably the increase of CO2 in the atmosphere was helping pretty much the establishment of citric plants above the cave. Because citric plants are very sensitive to the for the CO2 concentration in the atmosphere. Summarizing the interpretation of this site, it increased atmospheric CO2, increased the citric plants, which also help to stop the erosion of the cave, associated with more dry period, stop the erosion there, which help the soil fixation, or increase the organic matter, then you have more plants, which which help your soil fixation, increase the organic compounds in your soil and also your sediment. Then we try to use the other sites to apply the same methods, the same proxies in the other side to see if what we saw here in Jaraca Cave was only that, or also happened in the other parts of the continent. Then we test a site here, Lapa Safin Cave, in the other part of the savanna, the Brazilian savanna. So we have 2 sites in 2 borders of the Brazilian savanna, and which you see here, the δ13C for Lapa Safin Cave. This is the δ13C was presented before from Jaraguá Cave. I just reversed the scale. Now the lower value is here in the top. And both sites in the savanna place show the same shift here. The strongest from these 2 sites, which you see these dots, also present the same shift here, which follow the increase of CO2 in the atmosphere here during this time period. Okay, but then these 2 sites was the same kind of biome here, which was the savanna. So then we test another site here in northeast Brazil, where it's not savanna anymore. Here is Caatinga, which is a dry forest. This was work led by Gisele Urtida. And just a bit of background, again, in the southwest of Brazil here, we have this delta TO, which is going to more higher values to the Holocene. But when you go to northeast Brazil, we go to more lower values. There is a climate dipole on precipitation between this part here and this part here. So when the Holocene was getting drier here, it was getting wet here. And when you look at the Lapa Sinking Cave, which is in the middle, you see flat, basically. Not much different from the glacial period for the Holocene period here, because it's right in the middle of this dipole here. So then we are trying to understand the δ13C in this part here, which you see, not yet, but this was the condition of that cave today. This was presented in the paper of Gisele Urtida, 2020. You don't see much soil in the top of the surface of the cave. Chico presented this picture to you yesterday, so it's a very semi-arid region, not much vegetation, not much soil. All the soil was inside of, not all, but a significant part of the soil was here in some point in the past, was inside of the cave. And when we look at the δ13C, which is here, again, we have, not, but we see just the opposite, actually. We have more negative values during the glacial period until the mid-Holocene, to be more precise, until 4.2 here. And when this dry condition was established, when you see we lose this vegetation here, and then the values of the δ13C here also get near to the bedrock values, which is this small star here, these black dots here. Okay. But here, the δ13C follow pretty well the δ18O. The δ18O point for more wetter conditions here, going to a drier conditions, when we also have the δ13C value shift here. Okay, so it was getting more dry, you get less vegetation, less soil as well here. This time the δ18O, δ13 was connected. The strontium follow the δ13C, like the other sides. And again, when you look at the pollen records of that region, we also saw the vegetation changes here. And get to the end of my talk here, but just to have some context, the Caatinga look like this dry forest. The savanna look like this, when we have more forest, more open fields. And we see this in the δ13C today in stalagmites of these two different places. So this is the situation above Jaraguá Cave today. This is the situation above Urbu Cave in northeast Brazil today. But when you look at our records, this indicates to us during the glacial period, this place was looking like this, or in these places, in the glacial period was looking like this. It was kind of a big change. Well, not really, but like I said, more in the direction of that. I'm finishing now, so this is my last slide. All these three sites I was presenting here was presenting these two papers here. It started from Jaraguá Cave, the Lapa Sem Cave here was wrote by Victor Azevedo, supervised by Nicholas Strix, and the Northeast Brazil was led by Gisele Tida here. So thank you. So I'm open for questions.